Hi, I am Anurag from Max Planck Institute for Informatics. Our work is titled Weakly-Supervised Domain Adaptive Semantic Segmentation with Prototypical Contrastive Learning. This is a joint work with Yongxin, Dengxin, and Bant. Let's start with the motivation of our work. There is a huge performance gap between supervised learning for semantic segmentation tasks and unsupervised domain adaptive semantic segmentation, or UDA-SS in short. The figure on right shows this performance gap where there is around 10% mean IOU gap between state-of-the-art unsupervised domain adaptation method like ProDA, DASS, CoreDA, and supervised learning. In order to reduce this performance gap, we propose to use cheaper weak labels from the real domain such as image, point, and coarse labels. We can see on the right that with the additional cheap weak labels, the difference in performance can be bridged with the less budget. The task is thus called Weakly-Supervised Domain Adaptive Semantic Segmentation, or WDASS in short. There has been few works in this direction, however, with following shortcomings. The prior works ignored the source target feature alignment using the weak labels for adaptation, and also they don't have a common framework that can work well with all the weak labels. In our work, we solve these two problems and is able to bridge the gap between supervised learning and UDA with less budget. We provide the following contribution for this work. First, we provide a common framework for WDASS tasks for different weak labels, namely image label, point label, and coarse labels. Our framework is mainly divided into two components, where we first aim to construct better prototypes using weak labels, and second, we perform alignment of features using the considered prototypes. Next, our framework is able to bridge the gap between UDA-SS and supervised learning. Notably, with coarse annotation, our framework outperforms supervised learning. Further, we also show cost versus performance trade-off for different weak labels, where point labels achieve better performance trade-off compared to other weak labels. Lastly, our framework achieves state-of-the-art on WDASS tasks for different weak labels. Let's dive into the framework for our work. The first component is about how to construct better prototypes with the guidance of additional weak labels. For a given training batch of images, we first collect the features from the encoder. Since we also have weak labels on the target data, we have two sets of features, namely features from pseudo-labels, which may be incorrect, and also features from the label points, which are correct, as we have labels for these features. In this example, we have pink feature space for sidewalk class and blue feature space for bus class. We show labeled pixel features as circle points and pseudo-labeled features as triangle points. We see some noisy or incorrect pseudo-label features as some pink triangles are in the blue feature space. Our motivation is to construct class prototypes which is less affected by these wrong labeled features. Once we get these features, first we compute an anchor feature for each class and the feature of label points by averaging these labeled pixel features. From the figure, we compute the sidewalk anchor feature as average of sidewalk label points denoted as circle points in the image. After that, we compute the prototype by weighted averaging all the pixel features, including the pseudo-labeled pixel features. The weight for each feature is computed as a cosine similarity of the feature with the anchor feature. We want to reduce the effect of wrong pseudo-labels. For example, the pink triangles in the blue feature space on the final considered prototype, and we achieve this by weighted averaging as discussed before. Next, we also perform image label correction, wherein for a class not present in an image, we correct the features by pulling away the feature from the prototypes of the classes present in the image. For this image, we pull away green triangles point features from the sidewalk prototype, which belong to a class not present in the image. This type of correction helps in making better features for the classes. The next important component of our framework is prototype-based contrastive learning, where we align the features. We have two types of alignments. First is intra-domain alignment, where we align features within each domain with their prototypes. This makes the feature space more compact for each domain. Next is inter-domain alignment, where we align pixel features from source image to target class prototypes. This is an asymmetric alignment as we align the features in only one direction, that is, from source to target domain and not vice versa. This type of alignment is particularly important for weakly supervised adaptation for semantic segmentation tasks, as we want to preserve the target domain features and have real labels from the target domain. Moving on to experimental setting, we evaluate our framework on standard UDSS setting on two benchmarks, namely GTA5 to cityscapes and Cynthia to cityscapes. Further, we have additional weak labels such as image, point, and coarse labels from the target dataset. We evaluate using mean IOU score and use TPLAB v2 segmentation network with ImageNet pre-trained network as used by prior works. We present the following quantitative comparison for the results. We compare our framework's performance with the state-of-the-art UDA method and supervised learning to show our method can bridge the gap between UDA and supervised learning. Further, we compare our framework's performance individually for each weak label with the previous state-of-the-art methods. First, we observe that our framework outperforms prior work and baseline by significant difference. Second, our framework is able to bridge the gap between supervised learning and UDA. And also, notably, coarse annotation even surpasses supervised learning with significantly less budget. Next, we showcase cost and performance trade-off. The x-axis denotes the annotation cost in hours, whereas the y-axis denotes the mean IOU performance. The colored plot shows performance of different weak labels under varying budgets. The black solid line shows supervised performance, whereas the black dotted line shows semi-supervised learning performance. We observe that the colored plots outperform supervised and semi-supervised methods with similar budget. Further, the red plot, that is for the point labels, performs better at lower budgets. Thank you for listening to my talk. You can get more details by scanning this QR code. Thank you.